here? Good, yes. So the circuit diagrams that we saw yesterday were a particular implementation, or the technical term that they use for it is the realization, right? You frequently see that mentioned, where when they say to realize a circuit, it really means to implement or to create the circuit. So the particular realizations that we spoke about yesterday used a single op-amp, and the network, the second order function was created by adding additional capacitors and resistors to the network that we had before. The approach we're going to take today is to create the higher order low pass and high pass filters by cascading first order sections. Now, this was a question somebody asked a week ago when we started to discuss if it was possible to cascade the op-amp filters that we made to create higher order filters. And I said yes. And this is how the discussion, this is what we're going to discuss at least for the first part of our lecture today. So, for instance, the first approach, and we'll also compare the approach to what was done yesterday. Of course, immediately, once you cascade the filters, if you take two first order filters to make a higher order filter, of course, you're now increasing your op-amp count, because you now have two op-amps in the circuit instead of one. All right, so again, as I mentioned yesterday, everything is always a trade-off. The designs that we used yesterday, the VCVS versions, would take a single op-amp, and you have you just build up on the network in front of it. But the component cost in terms of op-amp use is small. Once we start to cascade first order sections, and each section now is an extra op-amp that you have to use. Is that relevant? Of course, it depends. For our purposes, for design and talking about it in an electronics class, that's not an issue. But if you're in I guess in the world of manufacturing and you're making things to sell, the cheaper, well, maybe not the word cheaper, but the less expensive your prototypes are, the better the profit you are likely to make. So you will try to reduce the component count and use the smallest component count that will give you the sort of performance that you desire. Right? So it's always a trade-off. So let's see, if we want to create a higher order, and in our case, let's see at this point in time, a second order low pass filter, if we cascade two first order filters, so this is the transfer function for the first and the transfer function for the second, both of them have the same cutoff frequency, which is 1 over RC. Okay, so we put that there. So one is going to pass through one filter, and then it's going to pass through it again. So you combine the two transfer functions, and simple algebra will give us that the overall transfer function that we're dealing with now, back to the second order function, you have S squared in it. So we have the second order behavior here. And the circuit arrangement is like this. So you have a low pass, and then you're cascading it straight into another low pass. So the transfer functions are there, and then what you would expect, of course, this is a first order, so that the response is this one is minus 20 dB per decade, a roll off. This one has another minus 20 B here. But both of them are sharing the same cutoff frequency. Right? So what I mean, just intuitively what you can see. So you pass your signal, the signal comes in, and it goes through the first filter, and whatever is the input is subjected now to that sort of truncation, and basically everything above here is supposed to be gone. You pass it through the second op-amp, and it's going to impose another 20 dB cutoff on top of that. So it's going to take the same passband, hopefully, and pass it, but it's going to impose yet another 20 dB on top of this. right? So hopefully now we're going to get what we expect, which is a minus 40 dB per decade roll-off. Right, and what we could express it now. So we take the transfer function that we had before, right, and I'm going to just transform it into a slightly different version. Note this is very close to the second order, that second order standard function that we spoke about yesterday, right? The one with the a omega naught s over s squared plus 2 zeta omega naught s plus omega naught squared. Right? So again, in this case, you're seeing that it's the same sort of form, so it's going to behave the same sort of way, and we plot the frequency response on it, and this is what we have. As you can see, the blue line is giving us the first order roll-off. So each of those sections is going to give us a first order response. So that blue line is really the response of the two sections. You cascade it, so one is feeding the other one. And here's a red line showing you what the second order response looks like. You measure it on the graph and you can verify for yourself that it's rolling off at minus 40 decibel per decade. All right, and the roll-off frequency here is, you notice that the phase goes from 0 to minus 180, and we'll talk about that today in signals when we continue our discussion on the board plot to see how that phase arrangement actually comes about mathematically. But as you will notice, the cutoff frequency for this one is 100 radians per second, and the blue one is actually the blue one is set up so it crosses at 100. The red, which is the cumulative second order function, also crosses the in this case the 90-degree phase at the same 100 radians per second. Don't worry too much about that phasing. We're going to talk about that this evening to explain it a little more fully, but this is the important one up here. Make sense? Yeah? And we could compare the two versions that we have. So I have the standard version is the standard second order function is this character here. And then I have the two transfer functions here, one in green and one in yellow, right? So one of them is a single op-amp version, and the other one is the one where we just cascaded the two first order sections, all right? Which is which? I mean, all you have to do is to check back the slide if you have it available. Right, so one of them is the one which we did yesterday, the single op-amp version, and if you remember, this is the single op-amp version here. All right, and this one here now is the cascaded. So let's put this sort of response side by side. So the cascaded one is on the left, which is what we just did, two first order sections cascaded, and the direct realization, remember when I say realization, I mean the direct creation, which is what we did yesterday. So you take a second order passive network, which were the 2 R's and the 2 C's, and then you put a unity gain buffer on it to compensate for any impedance changes in the network itself. That's the direct realization. So if you look at it, you notice that the red line on the left, right, and the blue line on the right, the slopes are the same, the cutoff frequency is the same, but is there a difference that you can see or anything noteworthy? Look at the two diagrams. You're comparing the red line for the cascade and of course the response for the direct realization. Any immediate comment? Just like this is like one of those things where they give you a picture and they tell you there are 10 things wrong with the picture. No, not the curves versus the straight lines, right? But there's a little. What about the frequencies, Giovanni? Both of them have the same cutoff, right? Both of them. Okay, sorry. That wasn't what I meant. Yeah, my mistake. Forget that. I'm talking about the actual. Yeah, I'm talking about the actual curve itself. There's something about the curve. Look at here and look at here. And tell me what you notice about the direct realization. Higher frequencies. Okay, what I'm getting at is that you notice that when we did the direct realization, no, the response is the same. Both of them are sloping at the same 20 dB per decade because they are both second order. Sorry, at 40. They are both 40. So this is minus 40 dB per decade. This is minus 40 dB per decade. Both have the same slope. Both have the same flat response here. The issue is right in the green circle. Remember with the direct realization, what we said is that the pass band, the cutoff frequency, sorry, was the point where the amplitude of the pass band dropped to 1 over √2 of the pass band value. In other words, 0.707, right? Or in decibels, it dropped by minus 3 dB. Right, that is where the cutoff frequency was. If you, let me see if I can zoom in a little bit here. If you look in here on the one, the direct realization one here, the cutoff, we do have the cutoff frequency here. Get a different color here. This point right here, that line is very fat, but that drop here is minus 3 dB. If you go across to the one that we did this morning, on the single, each section here, each single order section here is giving you minus 3 dB. But if you look at the overall behavior, this point here is actually minus 6 dB at the cutoff frequency. Right, so one of the little differences that you have when you cascade is that each section at the cutoff is minus 3 dB. So you cascade 2, you're going to get minus 6. You cascade 3, you're going to get minus 9. Whereas in the direct realization, the cutoff frequency here, that attenuation at that point is always going to be minus 3 dB. Yeah? So that's one subtle little difference that you have to be aware of. The behavior of the circuit is the same. The transition, the roll-off is the same minus 40. The phase behavior is the same. But that little attenuation, that drop at the cutoff frequency is different. It is bigger for the cascaded version than the direct version. Everybody seeing that and following? This is a very small, it's a subtle sort of point, but it can, if you think about filtering very small signals, low-level signals, that could probably make a difference between the signal passing through and not, right? It's twice the attenuation. So you have to look at it that way. 3 dB looks like a small thing on a log scale, but remember 3 dB is 0.707 of what the passband value is, 70%. So 70% is attenuated by the time it goes through the first, sorry, 30% is attenuated. So you have 70% passing through about. And then when you hit the second filter, it lops off another 30 off of that. Right? So every time you go cascade a section, you're going to lose a particular percentage of what went before. Okay? So just bear that in mind. So now again, you're trading off one thing for the other. This design that we just did is very easy. Just think of the sort of approach for designing this, right? The op-amp, the two resistors and capacitors are the same, and you select them again like we did yesterday. You pick your cutoff frequency, you pick the capacitor, and you calculate the resistance value. And then you just assemble the circuit here. Yesterday, to create the first and the second order function, remember, if it's a low pass filter, the capacitors are equal, but one resistor is twice the value of the other one. So it gets a little bit more complex at that point. Right? So you have different values resistors in that case. Yeah? All right, so what about the high pass approach then? Right, and I'll leave you to consider that, but the same approach for the high pass filter. So what will be the transfer function? Right, you have to remember the transfer function for a single section high pass filter has a S on top, and it's an S plus something, right? S plus something. That's the standard form. All right, and well, of course, you know that in the case of the low pass filter, that is actually the cutoff frequency, right? This is just a rearrangement of what we are accustomed doing. So the high pass filter has a high pass filter has 1 0 and 1 pole. The low pass filter has no zeros and 1 pole. Okay, the first order section. So the transfer function is going to be two of these. This multiplied by another one looking like it. The cutoff frequency is going to be what? Is it going to be the same as each section or different from each section? Right, it's two sections that you're cascading. So each section has a cutoff frequency of omega c. So the overall high pass filter in this case is going to have a cutoff frequency of omega c. And what is the Bode plot or the frequency response for this filter? Well, exactly what we did for the low pass. Right, you have the cutoff frequency at some point here. So this particular response is going to look like that. All right, and what is the slope here? That slope is going to be what? How many dB per decade? $20, $40, $60, minus $20, minus $40, or minus $60? $40, correct, right? So this slope is going to be 40 plus 40 dB per decade, right? So it doesn't pass anything, and it's going to go up here until it reaches the cutoff frequency, right? And like the previous example, at the cutoff frequency, the attenuation at that point is going to be minus 6 dB, right? Whereas for the single op-amp version that we did yesterday, the Salin and Key version, the attenuation at cutoff is minus 3 dB, right? That's subtle difference again. All right, so yes, the first thing, so you could create, this is a fairly straightforward, it's a very easy design. The response is very flat, okay, and you can get reasonable performance for both the low and the high pass filter design by using this approach. The trade-off is that you're going to have an extra op-amp. Not too much of an issue most times, because you can get double op-amps on the same chip anyway. It does depend on as I say, on the particular application that is being used for. If price is an issue, then you want to reduce the number of components on it. right? This is using the same number of passive components. You have 2 resistors and 2 capacitors, right? But you have an extra op amp on it. Fair enough? Yeah, no, maybe make some sense. Yeah. Yeah, I know it's getting down in the semester and busy day, right? Brain food. Okay, so we've done low pass and we've done high pass. So now let's have a chat about band pass filters. Now, band pass filters basically pass signals at only within a certain range of frequencies while rejecting everything outside of that particular range. Now, if you think about it, almost all electronic circuits are inherently bandpass filters because they only process or work with a set of frequencies, and everything outside they're not going to respond with. So a typical audio amplifier, right, or a small signal amplifier that you would have learned to design, for instance, in level 1. It has a frequency range, so it will run from some low to some high frequency, and beyond that is not going to work, or outside of that is not going to work. Similarly, an audio amplifier that you have for your own use is supposed to pass frequencies between 20 hertz and 20 kilohertz, but it has a very poor response outside of those. So inherently, those behave as bandpass filters. The truth of the matter is that almost all electronic circuits, from very low to very high, are inherently bandpass filtering in their behavior. But what we're talking about here now is to intentionally make a circuit that does this. The response is that that figure below here. This is what the frequency response looks like. So it passes a range of frequencies between some lower and some higher range. And of course, we define that those cutoff frequencies, the low and higher frequencies are, of course, when the value drops to minus 3 dB of the pass band. Hence the term that you would have met, I believe, which is the 3 dB bandwidth for a circuit. I think you may have met that in electronics last time. So it is exactly that reason. So the 3 dB bandwidth, or the bandwidth of the filter, runs from the lower frequency to the higher frequency. And then there's a center frequency where the maximum output of the filter is obtained, right? And we call that the resonant frequency, or the center frequency, omega R or omega C. You're going to see both of them appearing, and you will know the context. The resonant is because of the fact that depending on the type of circuit, you may actually get quite a bit of amplification right at that point and nothing else. So the bandpass filter response looks like that. We call the bandwidth of the filter the range of frequencies between omega H and omega L. And then we also classify, and that's a little bit of a misspelling here. It's supposed to be filter, right? So you can change that. They're classified as either narrowband or wideband. If the bandwidth, in other words, that capital B here, if it's smaller than 0.1 of the resonant frequency, so wherever is that sort of center frequency inside of there, if it's less than 10% of that, they call it a narrowband filter. And if it's more than 10% of that, they call it a wideband. So for instance, an amplifier will be sort of a wideband bandwidth filter, if you want. The behavior is like a wideband filter. Narrowband filters would be the ones that are used, for instance, in radio circuits. So tuning, as we spoke before elsewhere, when you tune to a particular frequency to listen to it, the filter in the electronics that is locking on to that particular frequency is going to be a very narrow band filter. The omega R would be the one that is a carrier. So if you're tuning into to 90.1 megahertz or whatever it is, 97.1 megahertz, omega R is 97.1, but the bandwidth is very, very narrow around that, something like plus or minus 200K. All right. And then, of course, there's this Q factor that you met before elsewhere. And the quality factor really has to do with the ratio of the resonant frequency to the bandwidth. All right, so the better the quality factor or the higher the Q number is, the more it peaks at that resonant frequency value. All right. Now, there are many ways, there are many ways. There are books on this, and in fact, if any of you all do the network synthesis course in level 3, you're going to see a whole number of ways of realizing bandpass and filter characteristics. All right, most of them require a fairly complicated bit of circuit analysis, not anything that is beyond you by any means, because there are no integrations and differentiations in there. But you have to, the expressions tend to be a little bit long, and the algebra is a little bit tedious. Two types that are on the page is Salin and Key, which is that type that we've introduced before. There's a version here. Now, you still have the two capacitors, but you have an extra resistor in it, inside of here. And depending on the behavior, you will notice that C1 and R3 may or may not be in parallel, depending on what is happening with C2. That's on that side. And then on the right-hand side, we have one that is based on the Weinberg. You remember the Weinberg is an oscillator circuit. It's an RC in series and an RC in parallel. And this R and this C are in parallel because here is really connected to ground. All right, so this is the Weinberg circuit. We used it to make our sinusoidal oscillator some weeks ago, but here it is being used in a bandpass filter. The reason, of course, is that we know in the case of the Weinberg, that the Weinberg network is very frequency selective. That is how we were able to make the oscillator work, right? By selecting the values of C and R, we can make the, when we did the oscillator, we could make the Weinberg oscillator oscillate or resonate at, at a very precise frequency. So if you put that now into this filter circuit, what will happen is that as the input comes in and passes through, the Weinberg network will only resonate or respond to whatever the frequency is determined by R and C. And the rest of the components around there are really to stabilize that behavior, compensate for any losses, and send the sort of the filtered frequency on. The bandpass, which has to do with exactly what the Weinberg is set up to do. All right, we're not going to spend time. Those are discussed in more advanced courses on the network synthesis course, for instance. So what we're going to do is to create them by doing what we did in the earlier part, which is a cascade, some first order low pass and band pass filters, and to create the band pass. The band reject is not so much going to be cascaded, and you'll see that in a little while. So hold on to this with a little grain of salt here, right? So we're going to create a band pass filter right now by cascading a first order high pass and a first order low pass. So this is the low pass filter here, and this is the high pass filter here. And you can already see how that is going to work, right? Even without doing any maths, once you understand what the behavior of the circuit does. So we have a signal coming in here. It passes through the first one, which is the low pass filter. All right. So it passes through the filter there, and as it passes through, you have this response. Okay, that heads on to the second one, which is a high pass. It doesn't actually really matter which way you do it. You pass it now to the second filter. The second filter takes this signal now, but it imposes that sort of frequency response on it. So the only thing that survives, okay, is going to be this little bit in the middle. So nothing here, nothing here. And we have this little band that is passed inside of here. Okay, it doesn't really matter which sequence you do it in. What matters is where you set the cutoff frequencies for the high pass filter and the low pass filter. All right? Yeah? No, maybe? Looking usable? Yeah? Once you understand intuitively what the filters are doing, then the rest is easy. So this is the expected frequency behavior. So the high pass filter section will give the response on the left hand side. The low pass filter is going to give me the response on the right hand side. One feeds the other, or the signal goes from one to the other. It doesn't really matter who is first, except what you have to figure out is where the cutoff frequencies are. So this is what we expect the behavior to look like. So here we go. So the transfer functions, we had those before. The high pass filter is the one that determines the lower cutoff frequency. And the low pass filter is the one that determines the higher cutoff frequency. Why is that? I mean, the answer is kind of right there, but why is that? Remember the sort of response that we want. The response is supposed to look like this. Okay, so this section here, this is high pass filtering behavior, nothing, and then it starts to pass. But this is a low end of the bandpass filter response. So the high pass filter is determining the lower frequency band. This where you pass and then you stop, that is low pass filter behavior, but that is actually the high pass, the high cutoff frequency for the filter, right? So each filter, it has nothing to do with the design of it, but what we are using it for, we're using the high pass filter to set the lower end and the low pass filter to set the higher end. Yeah? And of course, the design sections are easy, right? The low pass filter, which is the equation here, that is going to determine the higher cutoff frequency, and the cutoff frequency for the low pass filter, you know is 1 over R1 C1. We did that last week. So omega H is 1 over R1 C1. And the high pass filter, which is the one with the 0 and the pole, that is the cutoff frequency for that is also 1 over RC, but for this particular one is determined by the filter, the capacitor and resistor value for that particular one. So you put them together, they are cascaded, which means that the transfer functions multiply. So if you multiply the transfer functions, the overall bandpass is the transfer function of the low pass section multiplied by the high pass, which is this, or this, right? One version has it in terms of C and R, the other version has it in terms of omega L and omega H. Okay, this one is just a little easier to keep writing. So you simplify, and this is what the bandpass filter transfer function looks like. Notice it has 1 0 and it has 2 poles. Yeah, 1 0 and 2 poles. So we take that, and the general form, if you go in the literature or the handout that I gave you, you will see that the general form of a bandpass filter transfer function looks like this thing in gray, right? It has 1 pole, it has 1 0, and it has 2 poles. And what we can do, like we did before, for the what do you call it, the second order low pass filter case. Just now, excuse me a second, please. Hi, yeah, sorry about that. Okay, so it's Christmas time, so telemarketers are on the line, you know it is. So here we have the general form of the bandpass filter transfer function, and what we have below in yellow is what we just derived. So it's very easy to compare the two coefficients now and see that the cutoff frequency for the bandpass filter is given by the square root of omega L by omega H. And of course, each of these you determine by your own thing. You remember omega H is a low pass filter response, right? And that's 1 over R1C1. And omega L is a high pass filter cutoff, and you determine that by 1 over R2C2. So you have control over all of that. So you pick both as before a design approach is a pick both, and you just put in the values now and you have your circuit design. So let's test the thing, test the theory. So let's say we want to make one, and in my case, I'm using the design where omega H, in other words, a lower cutoff frequency is 100 radians per second, and omega L, actually I should have this the other way wrong, the omega L, my mistake, right? This should be omega L and omega H, right? So you please swap these two for me, right? In the calculation we use omega L with a high pass filter and omega H with a low pass, right? So sorry about that, I'll correct that. So we set the low frequency at 100 radians per second, and we set the high frequency for the low pass filter at 1000 radians per second. The blue line is a low pass filter. This the first order low pass filter response is the blue line, and the red line is the first order high pass filter response. So we plot both of them on the same diagram so you can see now, and then we add the two responses, which is what the cascading will do, and this is what you have as the overall response. All right, let me just circle these here to make swap. So when you look over the recording, it will remind you to make that change as well. Okay, so you look at the overall response now, and you see that the orange line, the yellow-orange line, that is the frequency response of the bandpass filter. So it's passing everything. The cutoff, the 3 dB bandwidth is between 100 radians per second and 1000 radians per second. And then the resonant frequency. The resonant frequency is supposed to be, according to what we just did, omega R is supposed to be the square root of omega H by omega L. Okay? So the square root of 100,000 is what? The square root of 100,000 . Right, so it's supposed to be somewhere around 316, as I said, you just said 316 radians per second. So let's go and zoom in on this thing a little bit. Remember the bandpass now is at this point where the phase drops from, is starting at 90 and it's going through, it's passing through 0 and it's going to minus 90. This here is right where the cutoff frequency is when it passes through 0. And if we zoom in inside of there a little bit, all right, we zoom a little bit, you're going to see this is 100, this is 200, this is 300, this is 400. So that point is somewhere between the 300 and 400 mark. It's kind of hard on a log scale to check it. As I told you, the log scales, when you have fine graduations, is difficult to visualize or to actually get the value. But clearly you're seeing that the value here is somewhere between 300 and 400. And of course, well, we know it's going to be the 316 that we checked, which is right here. Yeah. So it seems as though the theory is working. Yeah. So test the theory, and the theory works. So any questions on that? Make sense? Or anything not clear? You all right? Yeah, seems legit. Except for the fact that I have WH and WL on the wrong side, but anyway. Okay, so that's the one way. So we make the bandpass. We can make the bandpass filter a very simple, straightforward design by cascading two first order a bandpass, sorry, a low pass and a high pass first order active filter. We could do that. And in this case, it's actually simpler than some of the previous designs that we looked at. For instance, these two here, the Weinberg requires two op amps, so we haven't gotten more expensive than that. Our design needs two amps, two op amps. The Salinan key has one op amp. It has 3 resistors and two capacitors to it. We're using 2 resistors and 2 capacitors, so we're using less resistors, but we're using one more op amp in this case. All right, so it's a trade-off, but the design and the response is very easy to derive. It's very easy to calculate, okay, without doing a lot of complicated network analysis. Right? Fair enough? Yeah? All right, something so. Okay, so we have a bandpass. So the final category of filter that we have to look at now is a band reject, right? Or notch filter, or I think I may have had it elsewhere, the band stop, right? So you see all of those terms: band reject, band stop, notch filter. Notch is a term that we kind of use a lot, fairly commonly. You may see it around the place, but if you see a notch filter, it's the same thing as all 3 terms mean the same. Okay, so this particular one now is used, this type of filter is used to stop a particular set of frequencies. One application, for instance, is noise rejection. If you are in an environment, a signal environment, for instance, where you know that there's a particular noise signal that will be around. For instance, in our environment, there's a 60 hertz, because our distribution system, our AC distribution system is a 60 hertz grid here in Trinidad. There's a lot of 60 hertz background noise. And if you're doing precise measurements of signals around the place, and you're not careful about it, that 60 hertz signal is inbuilt to the signal that you're trying to measure in the first place. And what you would get in many times, if you look at small signals on a scope and you haven't shielded it properly, is that you get, let's say this is the signal that you want to see on the scope. Because of this 60 hertz interference, when you do it in the lab, you will get something looking like this, right? Where the signal is there, but in the background, it is riding on a 60 hertz signal. So here's a situation where the red is what you want, the blue isn't what you want, or the blue is what you want to get rid of. So this is a situation where you could pass this through a notch filter, and the notch filter or the band reject or the band stop filter will be designed to remove the 60 hertz signal, but let just the red one pass. And there are many other applications for this. We had mentioned one, two about the feedback noise that you hear sometimes with auditorium and public address system speakers. Those are automatic notch filters. They're either automatic or manual. The automatic one looks for the particular frequency that is causing the feedback to occur, and it creates a filter automatically at that frequency and removes that from the sound signal temporarily. And as soon as the feedback goes, it turns itself off. Or manually, that somebody will sort of look at the board that they have in front of them, and they would see that a particular frequency is suddenly getting, the amplitude on the meters are getting very high, and they will just quickly put the gain down at that frequency to shut it off. That's an example of a band reject filter. And there are many, many others in audio and video application, in automotive applications, and communications, and so on that you're going to meet, right? But how they work, again, the same principle is there. It's going to, it has a center frequency. It rejects everything around that center frequency. So it's like the opposite of the bandpass. There's a center frequency and a bandwidth. The center frequency is what is going to not allow, is what is going to reject, or what it is going to stop. And the bandwidth, of course, is how wide around that particular frequency it is going to stop everybody. And then outside of that, it lets the other frequency pass. In this case now, we can't cascade. If we're creating this way with using the high pass and low pass filter sections, we can't cascade them. We have to run them in parallel, like the diagram says, indicates below. Why is that? If I were to cascade it, I can't. I mean, intuitively, this is what you want. You know that the low pass filter is going to give you that, and the high pass filter is going to give you this. So if you put the two of them together somehow, what you're going to have is that in everything is going to do something like this, which is hopefully what you want. So the missing part, or the notch, will be there. But you can't simply run it like that, because if you were to run a signal through the low pass, let's say we run it through the low pass filter to start with, then what's going to happen, if we run it through the low pass filter to start with, yeah, let me just see. Well, almost discontinuous bandwidth, yeah, in a way that's in the ideal case, that's what's going to happen. If we were to run the signal through the low pass filter, the low pass filter is going to do this and not let anything else pass. Okay? If we run it now through a high pass filter whose cutoff frequency is here, nothing, you're not going to get anything, because they already lopped off everything below that. So there's nothing for the high pass filter to let pass through. So all you're going to get is a low pass filter behavior. And it doesn't matter if you swap the things, because all you're going to do when you cascade them like this is to create the bandpass filter behavior, which is what we did before. What we have to do instead is not cascade them, but run them in parallel. So look what's, and add it up after. So this one here, we have the same signal coming in. It goes to the low pass filter, and this bit comes here. It goes to the high pass filter, and this bit comes here. And then if we sum the two of them, we now have this bit plus this bit, but whatever was missing in the middle is now gone. Fair enough? Make sense? Good. So if we do that, then once you understand that, then the arithmetic becomes, or the algebra becomes very easy. So here it is. You have a low pass on top, you have a high pass below. Of course, we're going to have one extra component here, which is this summing amplifier. right? Now it's not too bad. The conventional arrangements for the notch filter typically require at least 2 op amps anyway. So we are creating one here, but we need a simple summing amp to go with it. And you know how to create that already. That's a very easy operational amplifier application. So the circuit arrangement is like that. So from before, we have the low pass response here. Right, remember the low pass has 1 pole and no zeros. The first order high pass has 1 0 and 1 pole, and we add up the outputs here. Before we multiply them to create the bandpass, to create a notch, you add it up. So you add the 2 responses, and right, so you have response 1 and response 2 added. I put it in the form because omega for this one, the low pass filter, remember omega L is 1 over RC, so I could substitute RC for omega in both cases. So I get it into this form now. So that is a transfer function for the notch filter. Notice this one now has 2 zeros and 2 poles on it. Typically, the zeros are complex. Right? For the bandpass filter, the zeros tend not to be complex. Remember, the bandpass filter, the high pass filter has 2 zeros as well. The second order high pass. So I have that here. There is a standard form, a general form for the notch filter as well. So all of these filters, and that's one of the things, and we'll put that down in the problem sets for you to recall. All filters have a standard form of the transfer function. Okay, so this is the standard transfer function. Notice it has the 2 zeros and the 2 poles. This is our version here. Right? The main difference between our version and the standard version is that their zeros here. If you look at the zeros, to get this to work, you have to have the zeros at plus or minus j omega r. All right? So that's how we get the s plus the s s squared plus omega r squared on top there. In our case, our poles, and we'll again when we talk about a little bit more about the board plot this evening, our zeros, sorry, are a little bit are complex as well. So it's plus or minus j something, but they have moved around. Plus or minus j omega r, if you remember, if you have your real and imaginary axis, plus or minus jr is going to be just on this axis here. Our design puts the zeros somewhere off on this side, right? So it's imaginary, but they also have a real component. Just a little mathematical talk is not anything for us to be complain about at this point, because it's not part of what we're discussing. But the important part are the behavior of the poles. Remember, the poles are the thing we mentioned before. The poles are the components of the transfer function that determine largely how the frequency response is. And if we compare the standard form here, we are again going to see that the resonant frequency is the square root of omega L, omega H. Right? The same behavior that we had for the band pass, we're having for the band reject or the notch filter. Okay? The transfer function, the denominator is almost identical. The numerator has the extra 0 on it. And we can test the theory again. So here's one where the lower frequency, omega L, is 10 radians. The higher frequency is 1,000 radians per second. Notice the behavior now. Right? This is the notch. So you substitute it first off, and you get the transfer function here. This is what the transfer function looks for that particular design, and look at the frequency response. You see what it's doing, right? So it's passing everything, and then it's rejecting a group between 10 radians, right, and 1,000 radians per second. So everything inside of here is going to get rejected. Everything outside of that is going to pass. right? That is a notch or the band stop or the band reject behavior, right? Just keep a little eye though on the phase response. Notice, and we're going to talk about that the last couple of slides that we have. Notice that the phase is really lousy. It starts and it goes all over the place. Right at the notch, the phase of the signal is changing from a minus angle to a positive angle, and then it goes its way again. We'll talk about that in a second, but that is one of the consequences of notch filters, that the phase gets very lousy. But the behavior, which is the frequency response, just by cascading not cascading, parallel, putting a low pass filter and a high pass filter, a simple first order low pass and a simple first order high pass in parallel, we have created a band reject filter. Yeah? And the arrangement, how you derive the transfer function and how you implement the transfer function is very straightforward. It's not complicated at all. Following? Yeah? Good. So last couple of slides here as we discuss something called phase now. Now, one of the things about it is that if you recall from when we did the Fourier series discussion elsewhere, and when we spoke about it inside FA, and we met it a lot, once you have signals going through a system, a signal has a magnitude. Once it has any frequency component, each component, and we saw that once the signal is periodic and continuous, the components are all sinusoid components. So all of the sinusoids have an amplitude, a magnitude, and they all have a phase, which is how each of them relates to each other. The sort of timing, for instance. So an audio signal, for instance, how an audio, like the note from a piano. When you play a note from a piano, you play a note from a guitar, the frequency, the range of frequencies, it is what determines that it is a sharp or a C or whatever it is, or a B flat. The frequencies in it determines that, but the phase relationship between those frequencies is what makes the C sharp on a piano sound like a piano, but the C sharp on a tenor pan sound like a tenor pan. The same frequency components are there because they are C sharp, meaning that it has a particular component or component in there somewhere at a frequency and at an amplitude, but the phase relationship to the other ones is what makes the C sharp on the pan sound like a steel pan, and the one on a piano or guitar sound like a guitar. Same thing for our voices. A singer, two singers can sing exactly the same notes in a song, but which means that they are releasing the same frequencies to the audience, but the phase relationship of those frequencies makes one sound as a tenor and the other one sound as a soprano, for argument's sake. And that happens in almost any situation where you have a whole bunch of frequencies coming through. Once you are dealing with a spectrum, and the spectrum defines the characteristics of the signal, then the components are always there, but the phase relationship is what basically, as we mentioned before, that phase relationship is what creates the signal to mean something in one context and not another. Now, when you filter, which is what we've been talking about the last couple of weeks, when you filter, you are removing frequencies. Fine, you're getting rid of something that you don't want. But the expense of that is that you upset the phase relationship of the remaining components. And look at the diagram that I have there. That was the notch filter that we just did. So passing it through the notch filter, the upper diagram shows the frequency response. So I'm removing a bunch of frequencies and I'm passing a lower band and a higher band, which seems all well and good. But look at what has happened to the phase relationship downstairs. The phase had some sort of behavior before the notch. Right at the cutoff frequency of the notch filter, it changed very suddenly from a negative to a positive phase, and then it continues in the positive direction. And remember, a phase change of something like a negative to positive is like an inversion. If you go from minus 90 to plus 90 or minus 180 to plus 180 kind of thing, you basically reversing the signal. And if you think about it, so let's say this was someone's voice, and there was something happening, for instance, a background noise that you wanted to get rid of. You put the notch filter on the microphone that they are talking or they're speaking through, and then you pass it through the amplifiers and you go their way. After it's filtered, it's going to sound different, right? It may be a very drastic change, or it may be not. Sometimes we do it intentionally to make things sound differently, right? As a special effect, for argument's sake, right? And I don't know if any of you all, just now, Sadie, I'll get to that in a second. If you've ever listened to your own voice recorded, right? I don't know if you've listened to yourself recorded. Do you like how you sound, or do you like, or does it sound strange? Yeah, it's different to us because your voice sounds like a different person. You hear yourself, your brain and your skull and everything else in between is a bandpass filter. So when you speak, and by the time it gets through to your ear and you hear yourself, you're hearing yourself with a mixture of sound coming back out in the atmosphere, back to your ear, and transmitting through your body internally. Your ear combines that, and there's a bandpass and a notch filter sort of behavior there. But when you record it, the recording is not picking up the influence of your head and body on the sound. It's just hearing the part that went out to the atmosphere, which is what everybody else hears. Okay, and that behavior, your body, for instance, would have done a phase change on the signal. So when it mixes back with everything else, you sound quite different. It's the same behavior here. So once you filter, you adjust the frequency components, and you may or may not drastically change what is passing through. Your intention was good, which was to filter, to remove something unwanted. But the result is that in removing something unwanted, you create something else, which is a distortion in the phase. Sadie, no, when the vehicle passes and the sound, that low and higher pitch, that is a Doppler effect that they're talking about. Is because the vehicle is moving. It's not a filtering effect. It's changing the speed of sound relative to the vehicle. So when it approaches you, the sound is moving at because the vehicle is moving towards you, the frequency of the sound changes pitch to a higher frequency. So you hear that, and then when it moves away from you, it's subtracting the speed of the car away from you. Right, so that's a little bit different. There is a phase change at the point when it passes you, when it's changing from one frequency to the other. Yeah, all right. It is a bit of frequency shifting. Yes, exactly. Yeah. So altering it creates signal distortion, and it may or may not render the filtered signal useless, which is why there are so many different ways to implement filters, transfer functions. And just a couple of them that I put up there, the one that I mentioned, but you wouldn't do that until you, if you do the 3024 course. The Butterworth type transfer function is nice and flat. It changes gradually from the passband to the stopband, and the phase response is reasonable. It's kind of gradual and it's fairly predictable. The Chebyshev type filters has a ripple in the passband, so it bounces around a little bit, but it changes very sharply from the passband to the stopband. So for certain applications, if phase is not important, and getting rid of something unwanted is the important characteristic, then you would use this filter. The phase response is poor. And then, like in the audio world, they use filters called Bessel filters. You would have probably met that term already, a Bessel function. Well, the Bessel filter is like the Butterworth. It has a nice pass band. It has a gradual change from pass to stop, right? In fact, it is more gradual than the Butterworth, but the phase response is excellent, right? It has a very nice linear change. And there are at least 10 more types of filters that people have created, filter transfer functions people have created to give this sort of phase behavior. All of them have an advantage and a disadvantage, and that is where engineers who have to do this kind of design have the choice to make. All right, so depending on where you land up in your working life or your career or your hobby, right? If you're doing certain things, you're going to have to take all of these little nuances into consideration. And this brings us to just a couple of slides on the very last type of filter. We're not going to design any of them, but just for your sort of knowledge on something that you're going to meet, something called an all-pass filter. An all-pass filter, now that sounds kind of counterintuitive. Well, what on earth would I make a filter that passes everything? Then don't put a filter in the first place. Well, what happens with the all-pass filter is that it actually lets everything pass without any amplitude distortion, but it shifts the phase. So they sometimes call the all-pass filter a phase shifter. And they use that in communication work, especially to correct the phase distortion from other filters. Or for instance, for transmission lines. You're going to learn transmission line theory sometime probably from next semester and the like. A transmission line, which is the lines that carry high frequency signals, there's capacitive, resistive, and inductive behavior going down the road. So it acts like a very complicated passive filter. So there's amplitude distortion and there's phase distortion around the place. So these all-pass filters actually correct the phase, if properly designed, can try to correct the phase change that another filter would have created to get you back to a situation that you wanted to be in before. And if you look at this, look at the kind of transfer function here. So it's a single pole. This one is a first order. So it has 1 0 and 1 pole. The second order has 2 zeros and 2 poles. And they are almost complex conjugates when you design them. The response of that filter, if you look at it, looks like that. The magnitude response is flat all the way through. So it's not going to give you any gain or attenuation at all. But look at the phase response for this one. It's starting at plus 180 and it goes to 0. So if you were to combine that with a filter that we just designed, right? Let me see if I could pull it back for you. Look at this response. This phase response here is going from plus 180 here to 0 here. And if you go back to one of the filters that we had before, we just did early on in the class, or that I have this on a previous slide, slide 10 from the previous lecture. Right, this one. Look at this response for the second order low pass filter that we just made. The second order low pass filter, the frequency response is going from 0 to minus 180. So it's stopping a band. So we have a nice flat pass band here. It's rejecting something that we don't want, but at the same time, there's a phase response that is changing from 0 to minus 180. We just saw that I could create a filter that does the reverse, that goes from plus 180 to 0. So if I were to go back to that little design that we had there just now, and put now the other one that is going from plus 180 to 0, so that one is going to go from plus 180, and I'll draw, well, let me draw it on top of this, right? So just ignore the, let me just clear the garbage here a little bit. If I were to put, just imagine on top is a phase diagram, right? So if I were to put one that is going from plus 180 to 0, if I add that to this, right? Then I could compensate for it. So this one from here, actually, if I, sorry, I'll have to invert the signal, but you see, if I have one that is going from 0 to 180, which is like what the all pass is doing, right? Forget this one here. But if I add this to this, what I'm going to get is a nice flat phase response. So in other words, I could correct this behavior by adding a phase shifter like this to the circuit. Another op amp, and maybe inverting because I have to flip this around. I have to flip this response around. What I really wanted is to do this, okay? But that's fairly trivial to do. And if I add that to what I had before, I'm going to get my nice flat amplitude response. I'm going to get a nice flat phase response as well. Yeah? So again, everything that you do, as I said, there are consequences and advantages and disadvantages everywhere. So the last sort of general purpose thing that you like to do always is that if you make a change, remember that if you're doing a circuit or you're designing a system and the system makes an unwanted change somewhere, always try to find a way of resolving the unwanted change. Design and engineering is about changes and designing things to meet requirements. So when you have unexpected requirements, those are the kind of things that lead to trouble. So what you do in your design is to correct any unexpected consequences at the same time. Yeah, it applies to life as well, right? You always try to correct the unexpected consequences as well. So same thing here. So the last, we didn't do the design, but just as a comment on it, because this design is a little bit more complex than, and it's not part of our particular syllabus this time. But having created low pass, band pass, low pass, high pass, band pass, and band reject filters, all of them have a phase response that leads to some sort of distortion. So there is a corrective measure that can be taken, which is something called a phase shifter or an all-pass filter that does nothing to the amplitude, but attempts to correct the phase distortion that might have been created. Yeah? Right? Lots of talking, but basically that brings us to the end of our topic on active filters. We did the 4 categories, which were the low pass, the high pass, the band pass, and the band reject filters. We did the first and second order in both the low pass and the high pass. In the case of the second order filters, we created second order filters using the single op amp approach, which was the Salem key technique. And we analyzed those circuits, and then we created them using cascaded filters for the band pass and parallel filters for the all pass as well. Those were easier to create and easier to analyze and design. And then we spoke about a notch filter as well that was required. We did the design for that, a particular version of the design. And all of them, we spoke about the standard form of the equation. So the standard low pass first order and low pass high pass, and high pass first order. The standard second order low pass, which was a transfer function that we had met before in another course. The standard second order high pass filter, the standard form for the band pass, and the standard form for the band reject filters. So we covered a lot. The early analysis we did, because it was fairly straightforward, we did it using circuit theory. And then as we sort of learned the behavior going around, we went from the circuit theory side of things into dealing more with this sort of frequency domain side. So once you knew how to design a low pass and a high pass filter, first order low and high pass filter, we use that information now to enable us to design higher order low pass, high pass, band pass, and band reject filters without having to do the complicated circuit analysis. Yeah? Right, so it's a bit of work. We have the recording, so I'm hoping that you all take time to listen to them as you review. Yes, there's a lot to review. What we did in the slides and so on is more the focus of it. The handout, but the handout is a little bit heavy, and is not apart from the examples that are there. You don't really have to pay too much attention to the handout. What we did and what are covered by the slides, and what are and of course the recording of the lecture itself is more than adequate to cover the material that we did. Yeah. So any last minute questions, concerns? Right, as Sadie said, that yes, there's a lot to work on. We've actually done quite a bit in this semester. There's a lot of material that we've covered. What I've tried as far as possible is to try to get you all to understand the behavior conceptually. So if we're doing something conceptually, what happens? So like in the case of the filter, simple things that the capacitors, the capacitors, what do you call it, stop low frequencies but pass high frequencies. So depending on where they are located, you get the low pass and high pass behavior being created in the particular configuration. All right. So the last topic that we have to cover now would be on feedback amplifiers, which we will start next week, and conclude everything. What I'm going to do, as I said, I know as you all go through the material, there will be questions that come up, there will be concerns that will come up, and so on. What I think I will do is maybe to create something like a Google Doc that will be shared with everybody. So as you have questions, you could go to the document and put your question, concern. Other people may see it, so it could form almost like a list of frequently asked questions on general concerns, and we can use that for a bit of revision and review when the time comes. Yeah. Right, so that way you don't have to, unless you have specific things that you can email me about, but if it's a general concern or a general issue that needs some clarification that everybody can benefit for, we'll have one shareable document, so you just go and fill in the information on it, and we will take that and use that as a sort of checklist going through, and maybe even for everyone to as a sort of revision list of the things to pay attention to as well. Yeah. All right, so that's it for today. Let me